Structure of HNO3. So the obtained nitric acid is 61%. By fractional distillation, we'll get 68. And by using dehydration, by using concentrated H2SO4, we can convert to 98%. Here in this HNO3, in this structure of HNO3, nitrogen is the central atom of an element, and its valency combining capacity is 4 only, but valency electrons are 5 are there. And oxygen, we know atomic number and electronic configuration, valency electrons are 6, here only 1 is there. First, take the rough idea about nitrogen. It is oxygen, and here again it is oxygen. Now it is again hydrogen, like this. Either here or here, anywhere we can take. Now among 5, 1 electron is bonded with oxygen, like this. 1 electron is bonded with oxygen. It forms one covalent bond, sigma covalent bond. On oxygen atom, 6 valence electrons are there. Out of 6 valency electrons, here 1 valence electron is bonded with the nitrogen. Then here number of valence electrons are only 1. Again it is bonded with the oxygen. It forms one covalent bond. So around nitrogen, among 5, 1 is bonded. Remaining 4 are there. Already among 3 unpaired electrons, 2 unpaired electrons are bonded with this. Now on oxygen atom here, 2 lone pair remaining balance. Finally, on nitrogen atom, 1, 2, 3 completed, remaining 2 are there. These 2 are donated to oxygen. It forms a coordinate covalent bond. Already on oxygen atom, 2 lone pair and 1 is unpaired. It is paired up and it gives a vacancy to get the coordinate bonds. Now this is the Lewis dot structure, or just a structural arrangement. If we can take a resonance for this, we can take a resonance structure as it is oxygen and hydrogen here. This is nitrogen. Here take coordinate bond and here double bond, that is resonance, that's all. Only variation is these 2. So by using these, we'll get like this. Double bond is present between nitrogen and this oxygen atom, or in this case between these 2. So resonance, on the basis of resonance, these nitrogen oxygen and nitrogen oxygen bond length is the same. That is 121 picometers. This is experimentally determined. Either here also same 121 picometers, near approximately. Now here the bond angle is 130 degree is. Now nitrogen and oxygen somewhat bond length increases because sizes are greater, that's why its bond length increases. Its bond length is 140.6 picometers. Your size is small hydrogen compared to this. So finally its length also less, that is nearly 96 picometers. Here between this bond angle is 102 degrees. Better you remember the values. In examination, generally they won't ask. Anyhow, remember this. Based on this, sigma bonds are here 1, here 1, coordinate bond also sigma. In this nitric acid, nitrogen atom undergoes sp2 hybridization. Because the number of sigma bonds are how many? Only 3. 1 s orbital, remaining 2 p orbitals. That's why sp2. If it is sp2 hybridization, geometry is planar geometry, trigonal planar geometry. Planar means that's why nearly 120 to 130 degrees. Geometry is clear. Structure is clear. Okay, structure of nitric acid. Then next one is properties. Your properties of HNO3, nitric acid. Your pure concentrated laboratory HNO3 is 68% by mass. 68% by mass present its nature in the laboratory. Pure is colorless liquid at room temperature it is. Now here in aqueous medium, an aqueous medium, it acts as strong acid, and it produces H plus ions. See here HNO3 when dissolved in water, concentrated HNO3, here it produces H plus NO3 minus 1 nitrate ion produced. React with this, it forms a H3O plus NO3 minus 1 is formed. When dissolved in water, it produces a proton donor, acts as a strong acid. According to proton transfer theory, this is a hydronium ion. It is. So this hydronium ion also called a hydrated hydrogen ion. In first PUC, first year 11th standard, in equilibrium we know based on acid-base theory, there are one of the most important conjugate acid-base theory, there will get this hydrated hydrogen ion concept. They are H3O plus. Now here in these properties, concentrated HNO3 acts as a strongest oxidizing agent. Here concentrated HNO3 acts as strongest oxidizing agent, OA oxidizing agent. Strongest oxidizing agent it is. And this oxidizing capacity, OA capacity of concentrated HNO3, very important, depends on first one is concentration. Second thing is temperature. Third one is nature of material. Used in this process. These are the three important points, depends on oxidizing capacity of concentrated HNO3. Here concentrated HNO3 cannot affect or cannot react easily with noble metals like silver and gold generally cannot react. So here are noble metals like gold and platinum do not react with this. So based on this, some important chemical properties and some metals like chromium and aluminium with concentrated HNO3 shows passivity. Passivity means do not react. Initially it reacts, but further reactions cannot take place. For example, here take here concentrated, this is concentrated HNO3. This concentrated HNO3 into this just inserted aluminum rod or maybe a chromium rod, aluminum or chromium strip is introduced into this. Here it acts as a oxidizing agent. Generally, this aluminum chromium do not show any chemical reaction with this. Passivity means chemically inactive. That is due to the formation of a thin film metal oxide on the surface of this aluminum or chromium. This is a thin film metal oxide. This thin film metal oxide, that is Al2O3. If it is a Cr2O3 is formed. Chromic oxide or aluminum oxide. This chromic and aluminum oxides do not react. These are do not react or do not take place further reactions. Further reactions do not take place. That's why these are passive. Passivity means do not react. But some metals, based on their concentration and temperature and the nature of material, some are reacts, and some are reacts means it gives the different byproducts or the different products based on their concentration, temperature, and nature of materials. Okay. Now here two important chemical reactions are there. One is chemical properties of concentrated HNO3 with metals and non-metals. Two are very, very important reactions. Yeah, one of the most important is with metals. With metals means copper and zinc metals. These two are very, very important. Then some are with the non-metals are there. I'll explain that non-metallic concept. Compared to balancing here, main what are the products liberated? That is very, very important. And also, your concentration is very, very important. Here the copper is reacted with HNO3. That is concentrated HNO3, or first take here dilute HNO3 on heating at certain temperature. So here the concentration is different. Same here the copper is reacted with HNO3 with concentrated HNO3 on heating, it gives certain different products. So the reactivity, chemical properties of HNO3 depends on concentration. Some cases diluted, some cases concentrated, and temperature. So with the copper and zinc, two conditions are there here, two properties are there here. So in copper, better you take here 3 moles of copper and 8 moles of HNO3 in dilute conditions. It gives like are the 3 CuNO3 taken twice plus water H2O plus, here will get NO, nitric oxide gas is formed in dilute conditions. Now here nitrogen atoms are here 2, 3 the 6, but here 8 are there. Remaining 2 balance, that's why take here the 2 moles. Hydrogen atoms are here 8 are there, here 2, that's why take here the 4 moles and everything is balanced. When it is concentrated, here 1 mole and here 10 moles, here will get CuNO3 taken twice plus 5H2O plus NO2 gas is liberated. Nitrogen dioxide gas, here 10 are there, out of 10 already here 2 completed. Then remaining here out of 10, how many required here? 8. 10 HNO3. If you can take like this, 10. So here instead of copper dilute and concentrated, if you can take your zinc metal, same conditions. Sorry, better you take 4 moles, not balanced here. See it? 4 means here 2H2O. Already here 2 are there. Take here it is 2 moles. It is balanced. Now clear? Now here the 1, 4 conditions. Here 3 and 10. 3 and 8. So here copper is reacted with dilute and also copper is reacted with concentrated. Then we'll get in dilute condition we'll get nitric oxide. This is nitric oxide, but here nitrogen dioxide. Nitrogen dioxide. Same instead of this here. Yeah, if you can take zinc plus HNO3, zinc plus HNO3, dilute conditions, then we'll get one gas. And the same thing here, the zinc and HNO3 concentrated, HNO3 on heating will get one condition. Now here also just like this, here we'll get zinc nitrate, ZnNO3 taken twice, plus water plus air will get N2O, dinitrogen oxide. This is. Whereas in case of concentrated, we'll get ZnNO3 taken twice, plus here the H2O plus here N2O. Sorry, NO2 is formed. Nitrogen dioxide is formed. This is dinitrogen monoxide. This is nitrogen dioxide. Nitrogen dioxide is there here. So these two are important reactions. Balancing here 1 mole, take here also 4 moles. Yeah, the same. Yeah, the 2 moles and here the 2 moles, same thing. In both cases, like copper and zinc in concentrated method is same. There is no change. Here also main product is nitrogen dioxide. Here also main product is nitrogen dioxide. Both are the same. But the variation is only dilute conditions. That's why these two are very, very important. These two are very, very important conditions. Take here 4 and 10 moles. Here the 4 ZnNO3. Here 5 H2O. Like here 8 are there. Remaining 2 balanced, here N2O balanced. Now these are very, very important. Maybe these two reactions, maybe they'll ask in objective. When copper is reacted with dilute HNO3, what is the gas liberated? What is the oxides of nitrogen liberated? They'll create option number 1. This is second option. This is the third option. Maybe fourth option is N2O3. Like they'll create 4 different options. So answer is this. If it is zinc, N2O. In a concentrated condition, both are the same. So like these chemical reactions, better you concentrate while reading HNO3 like these important reactions. Because obtained in all the cases, copper nitrate, water, common, zinc nitrate. But oxides of nitrogens are the main product. They are very, very important. To confuse the children, they'll ask based on these questions. Clear? With metals, clear. The next one is with non-metals. So the concentrated HNO3 also oxidizes non-metals to the corresponding acids, corresponding compounds. Here for objective, maybe if they'll ask no need to balance reactions, better you remember main important concepts. Here with non-metals, second one is with non-metals. Here non-metals are here 4 given in our syllabus: I2, carbon, here S8 molecule and P4 molecule. These are the 4 important reactions. For example, here the I2 is reacted with HNO3, concentrated nitric acid. It is concentrated. On heating, we'll get HiO3 like iodic acid plus here water plus nitrogen dioxide is formed. This is. Like carbon reacts with HNO3, nitric acid, and gives carbon dioxide plus water plus NO2 gas. Your S8 molecule react with HNO3. Now it gives your H2SO4 plus water plus NO2 gas liberated. Now here the P4 molecule reacts with HNO3. Now your H3PO4 phosphoric acid, water plus NO2 gas is liberated. Once we can observe all the four important chemical properties with non-metals, all the byproducts are same, or maybe products are same. Like water here, nitrogen dioxide, all are the same, but these are very, very important. So what is the main product when here the iodine is reacted with concentrated HNO3? What is the product obtained? Iodic acid, HiO3. Balancing based on that first year redox reaction balancing, we can easy to find out. But main in public examination, they'll ask instead of balancing, what are the main products obtained? Here with iodine, iodic acid, carbon dioxide, sulfuric acid, and phosphoric acid. These are the some important properties with metals and non-metals. Finally, here one of the most important chemical properties there that is very, very important for 12th standard or for PU level in laboratory for practicals. Already in first year completed in practicals, brown ring test is there, one of the most important tests. Regularly they will ask in objective as well as in theory or in any laboratory practical to find out the nitrate ion. One of the most important tests for nitrates. Brown ring test. Very, very important test it is. For PU level in the laboratory, this is a very, very important test, that is CT, confirmatory test for nitrate ions. Nitrate ions means here NO3 minus 1 ion. To find out nitrate ion, brown ring test is a very, very important test. So in a given unknown salt, maybe sodium nitrate NaNO3 or potassium nitrate, barium nitrate, this is barium nitrate, or strontium nitrate, like these are some important nitrates of metallic salts. So in the laboratory here, and watch glass they'll give unknown salt. This is the unknown salt. That unknown salt in 12th standard level or PU level, one cation is present, that is Br basic radical, and one anion is present, that is acidic radical. One basic and acidic radical. For example, that unknown salt is NaNO3. Now here Na plus and NO3 minus 1. This is Br basic radical. This is Ar acidic radical. Like strontium nitrate is there, for example, SrNO3 taken twice. It gives Sr plus 2 plus NO3 minus 1, 2 moles. This is Br basic radical and it is acidic radical Ar. So to find out this presence of nitrate ion in a given unknown salt is present or not, we don't know. That's why for that confirmatory tests. Now first here the PT preliminary test for that. Taking a test tube like in this unknown salt, it is unknown salt. Now to this add concentrated H2SO4 sulfuric acid. Just observe it. There is no observation. There is no gases liberated. Now to this copper turnings are added and heated strongly. Any reddish brown vapors are liberated. Reddish brown vapors are liberated. That indicates presence of NO3 minus 1 ion in a given unknown salt. Only a preliminary test, this identification test is, primary test is, when unknown salt is heated with just concentrated HNO3 without copper turnings, there is no clear observation, there is no any other gases liberated from these. That is generally absence of second group radical Br minus. But whereas to the same solution, copper turnings are added, copper pieces are added, Cu turnings, then heated strongly, then it gives reddish brown vapors, indicates the presence of NO3 minus 1. Either maybe like this, any one. That is identification. To confirm that, here brown ring test is there, CT for nitrate ion. This is the identification test. For this CT confirmatory test, first thing is better you prepare corresponding salt solution. This is first. Second one is freshly prepared FeSO4 solution required. Then third one is concentrated H2SO4 required. These three are very, very important to do the confirmatory test for nitrate ion. That is a brown ring test. So this is very, very important. Freshly prepared. Freshly means already prepared ferrous sulfate easily oxidizes. That's why while doing this test only, better you prepare FeSO4. In laboratory, FeSO4 salt is available. By using that salt, just to take distilled water and shake it, we'll get a clear solution. The obtained clear solution is called a freshly prepared FeSO4. See here, this is the one test tube. In this test tube, take unknown salt solution. This is unknown salt solution. Means this is the salt to this water is added, H2O is added. This is called a salt solution. Okay, prepared, first one. Second thing is taking another test tube. In another test tube, to this take FeSO4 crystals. Yellowish green color FeSO4 crystals are available. To this again water add it and stir it. It gives a clear solution that is called freshly prepared FeSO4 solution. While doing brown ring test, generally students they'll carry the experiment in one test tube only. They will take salt and they will take freshly prepared in one test tube only. They will add water and they'll stir it, shake it. That is wrong. Don't take at a time two salt solutions in one test tube. After preparing separately these two important salt solutions in third test tube, this is the third test tube. In this third test tube, equal proportionate. If it is 1 ml, take here also 1 ml. 1 ml. Then take equal proportionate salt to solution as well as freshly prepared. That is equal amounts, approximately equal proportionate. Take here the salt to solution. We don't know that salt containing nitrates or any other basic group radical. Salt solution plus FeSO4 solution. Then stir it. While preparing FeSO, just add 1 or 2 drops of H2SO4 to acidify that. Now the mixed equal proportionate mixed salt solution and FeSO4 in third test tube. In this only take an inclined position by using a holder like test tube holders like this, and take in another test tube concentrated H2SO4 Now this concentrated H2SO4 add drop by drop along the sides of the test tube. Like this is the holder. By using this holder, just add a concentrated H2SO4 drop by drop here. At the junctions of the two layers, this is the salt solution layer. This is the concentrated H2SO4 layer it is. So at the junctions of the two layers, whenever this H2SO4 interfere with this, at these two layers, there exists even a ring-like structure. Like this is at two layers are the junction at interference, that is phases. Here a brown ring is produced. Brown ring is developed. That indicates the given salt solution contain NO3 minus 1 ion. Clear confirmation. So while doing this experiment, carefully better prepare like salt solution and freshly prepared FeSO4. And while adding constant H2SO4, also carefully add one by one. People will do generally mistake at this preparation of these. At a time, people will take at a time in one test tube, they'll take salt plus FeSO4, then to this they'll add water, then they'll stir it, to this they'll add H2SO4 directly. On get, for this we'll get a black color solution. Black solution will get it. We can't identify. This is wrong. That's why separately salt solution, freshly prepared separate test tube, take a third test tube, in the third equal proportionate and clear solution, stir it, and to that in inclined position just add drop by drop. H2SO4 will get the a brown ring at the junctions of the two layers if it contain. Already we can detect the presence of nitrate by using some preliminary tests by heating test with concentrated H2SO4 and copper turnings. For this, very important thing is, this is the theoretical explanation. Main important thing is for objective and for any other competitive examination, very important thing is here. Very important thing is chemical reactions. This is a wrong combination. Leave it. Now in this generally nitrate salt means here NO3 minus 1 is present. And we are adding FeSO4 means plus 2 reaction. Plus 2 is there. Ferrous sulfate plus 2. And here the water we are using and sulfuric acid we are using. That's why here are the 4 moles of H plus ions. Here are the 3 moles. Ionic reaction. So while adding salt solution freshly prepared and by adding H2SO4, this chemical reaction mainly involved nitrate ion, ferrous ions and this H plus ions. It gives this ferrous converted into ferric oxidizes. The ability of nitrogen depends on Fe plus 2 ion. So to identify the presence of this mainly depends on concentration and ability of Fe plus 2. Then it gives like Fe. Here Fe plus 3 moles plus 2H2O, water molecule, here 2H2O plus here NO. This is the nitric oxide gas is liberated. This is a very important reaction. The liberated nitric oxide gas immediately absorbed by one complex. That complex is formed in the solution, that is FeH2O taken 6 plus 2. It is a complex is formed in this salt solution. Immediately absorbed by this complex is absorbed this NO gas, nitric oxide gas. Then it forms like one complex, that is Fe. H2O taken 5 NO power here plus 2 plus out of 6 mole only 5 moles plus H2O is formed. This is the brown ring formula complex compound. Yeah, the formed brown ring formula is here Fe H2O taken 5 NO power plus 2. This is the very important formula. The formula of brown ring formed in the detection or conformity test for nitrate ion is this is very important. Now here after this complex formation, so many such a chemical reactions and so many complex compounds are there in inorganic only in coordination compounds. One of the most important chapter there will explain IUPAC name, rules and regulations, how to find out oxidation state. Anyhow, for this I will write one complex, full complex, that is Fe H2O taken 5 NO power plus 2. This is the ion. These two ions are satisfied by, like this also we can write Fe H2O taken 5 NO SO4 also present. Also we can create because the sulfate ions are present in a solution. This is the minus 2, this is the plus 2. So an examination they'll ask like this or like this model. So based on this, IUPAC name and oxidation state very important. So here in coordination compounds, one of the most important chapter in coordination compounds, IUPAC name of a complex compound, rules and regulations are there. Anyhow, just a simple idea, IUPAC name of this compound like Fe H2O taken 5 NO power plus 2. For this IUPAC name is, it is a cationic complex because plus, there is no special ending, rules are there, 5 are there. Here its oxidation state is +1, nitrosyl. Now here we can write 5 are there, that's why its name is penta, IUPAC name, penta. Water means aqua or aquo, penta aquo. NO plus means here the nitrosyl. And then immediately we can write iron, that is instead of iron we can write nitrosyl ferrate or iron, nitrosyl iron. Your oxidation state is only 1 is there. Now your ion is there, that's why we can write its name is complex ion. Just remember the name in coordination compounds. Next coming inorganic unit, there are some important rules and regulations to write its IUPAC name. They will explain very clear rule. How to write its name, ligands, rules and regulations are there. This is the correct IUPAC name of this complex. If it is SO4 is there, instead of writing complex ion, better you write sulfate. Everything is same. Your penta aquo nitrosyl iron 1 sulfate. Everything is same if they'll ask. Now your 1 indicates your oxidation state of iron is +1. Very important. Your oxidation state of iron Fe in brown ring complex. Brown ring complex is equal to +1. Very important. So here how to calculate means here Fe H2O taken 5 NO power +2 is there, plus here we don't know, let us consider here X plus water molecule is neutral, that is 5 into 0, nitrosyl is +1, only 1 is there, plus 1 into 1 is equals to their oxidation state is +2. Now here the X plus 0 plus 1 is equals to +2. X is equals to +2 minus 1, that is +1 oxidation state. That we can write in a Roman number. +1 Roman number 1, +2 Roman number 2. Rule is there. There in coordination or the complex compounds will explain very clearly. Okay, this is the brown ring test. In our textbook only theoretical explanation, 2 reactions given here, but a clear information given how to identify Means first preliminary identification test, then confirmatory test, and everything about any objective, either CET or a NEET or a JEE. If they'll ask any objective, these are very, very important. Better you note down all these in our notes. Or with you available beside you, any textbook, better you note down there only in textbook. Very, very important. This is the Brown ring formula of Brown ring, IUPAC name, oxidation state. So what is the gas liberated? Everything important. Clear? Finally, only one simple concept about nitric acid uses. Just I'll 2 to 3 important uses I'll write. Just note down here. Use of HNO3 nitric acid. Use of HNO3 concentrated nitric acid. Once we can observe in first PUC, 11th standard, in benzene, nitration of benzene is there. First year, very, very important. Mechanism of nitration of benzene. In that nitration of benzene, C6 and H6. Here are concentrated HNO3 and concentrated H2SO4 used as nitrating mixture. This is. So here nitric acid, main important nitric acid in this nitration of C6 and H6 benzene. It create one electrophile, that is NO3, NO2 plus. Now here under these conditions, here benzene is reacted with nitric acid. In the presence of H2SO4 will get nitrobenzene, NO2 plus H2O is formed. Now here it create NO2 plus OH minus. It is electrophile, it is nucleophile. Either here or here, anywhere this hydrogen atom react with OH minus, water eliminate, and nitrobenzene is formed. Nitrobenzene. Not only this one, simple example in first year, variety of organic compounds are prepared by using HNO3, that is TNT, explosive, trinitrotoluene. So to prepare trinitrotoluene, here we can use concentrated. Nitroglycerin, also another important chemical substance which is used as explosive agents. Now here to prepare so many nitrogenous fertilizers, your ammonium nitrate NH4NO3 is prepared by using concentrated HNO3. It is used to prepare fertilizers, nitrogenous fertilizers. And here concentrated H2SO4 HNO3 is used as an oxidizer. Oxidizer in rocket fuel, very, very important. In rocket fuel, it is used as an oxidizing agent, oxidizer. And also finally, it is used in etching of glass, and also your pickling of stainless steel. Here, these are some important uses. To clean the glass apparatus, we can use concentrated. Etching means like we can use concentrated HNO3. These are the some important uses of HNO3. Better you read from textbook and note down all these. A variety uses are there based on this. So this is a complete explanation about nitrogen and its compounds. In 15th group elements, nitrogen, phosphorus, two important compounds are there. About nitrogen compounds clear. That is about dinitrogen, ammonia, nitric acid, and oxides of nitrogen, and some hydrates of nitrogen. About nitrogen clear. Then simple topic is present, that is about the phosphorus. Today I'll start phosphorus. I'll introduce. Remaining 10 minutes time is there. I'll introduce phosphorus, and I'll complete one of the most important compound of phosphorus. One more class I want to complete this 15th group elements in P block. Okay. First 15th group only somewhat big chapter, big units, and everything is new. Better you concentrate 15th group elements. Remaining elements almost all similar. Explanation is similar. Same introduction, preparation methods, properties of a related group, 16th group compounds, 17th group compounds, and 18th group. That's all. Okay. Next one is about phosphorus. Phosphorus. We know about phosphorus. This is the second element of 15th group elements. What is the atomic number of phosphorus? Atomic number of phosphorus. Add 8. 7 plus 8. 15. Group number and atomic number same for this. So the phosphorus atomic number is 15. Electronic configuration is 1s2, 2s2, 2p6, 3s2 and 3p, 315, and its outermost orbit there is a d orbital, vacant d orbital. That's why phosphorus shows some different properties with the nitrogen. In its outermost orbit here 3s is paired and 3p is unpaired it is, and 3d orbitals are vacant, like this is ground state electronic configuration. Whereas in other compounds, one electron may be excited from 3s2 to 3d, that is the first excitation state. That is 3s1, 3p3 and 3d1. Now here 1 electron, here 3 electrons, here 1 electron is there in d subshell, that is 1. Total unpaired electrons are 5. That's why for this maximum covalency is 5, and maximum oxidation state of phosphorus also plus 5. 5 is the covalency, combining capacity, and oxidation state is plus 5. Now here the 1s orbital, 3p orbital, 1d orbital, maximum shows sp3d hybridization. So it is sp3d, it shows a pentagonal, means trigonal bipyramidal. Trigonal bipyramidal structure. So I'll explain complete story about this. And here the phosphorus generally are two important isotopic forms, like 15 to 16, like 15 to 17, like isotopic important forms. And here the phosphorus isotopic forms shows here the allotropic forms. Allotropic forms of phosphorus, they are already given to you, that is white, that is yellow, pale yellow, like red, scarlet, violet, and black. These are the some important allotropic forms of phosphorus. This is the introduction about phosphorus. Now here the hydrides of phosphorus P. One important, that is pH3 hydrides of phosphorus. and some oxides of phosphorus, oxoacids of phosphorus. Before that, yeah, some important stories of oxoacids of phosphorus, some important oxoacids. So to explain oxides of hydrates of phosphorus and oxoacids of phosphorus, we want the story about white phosphorus and red phosphorus story. After that, white and red phosphorus, preparation method of hydride of phosphorus, then oxoacid. This is the complete explanation about phosphorus. First, we'll discuss about phosphorus, white and red phosphoruses. So here, white phosphorus, and here another one is red phosphorus, red P. This is that we make like a column in our textbook, paragraph wise given. While reading this white and red phosphorus, better you create like a table and better you read this white and red phosphorus story. Easy to remember. So the first thing is it is generally one of the most important. White means light white or pale yellow solid it is, and pale yellow solid, it is generally translucent waxy solid. It is waxy solid substance. We know here red, generally it is a red allotropic form, red phosphorus. Generally it possesses gray luster. It is shining nature, gray luster it is. Now second one is white phosphorus. It glow in dark. It glow in dark means it shows one important property, chemiluminescence. Chemiluminescence property. Easy to glow in a dark, but it is not. Do not glow in dark. This is. Third one is generally it is insoluble in water. That's why white phosphorus, white P is stored in water, H2O, but soluble in carbon disulfide, CS2, very very important, but soluble in carbon disulfide. Here third one, it is insoluble. It is insoluble in both water and CS2, carbon disulfide. Now here fourth one is here. Generally white phosphorus exists as a discrete tetrahedral P4 molecule, one separate molecule as P4 molecule. That P4 molecule bond angle between this bond angle is 60 degrees and has high bond angle strain. Bond angle strain. Due to the bond angle strain, due to this, here the white phosphorus, white P is more reactive than red phosphorus, than red P. Here it exists, red phosphorus, it exists as polymeric tetrahedral. Polymeric tetrahedral link takes place, tetrahedral linkage. Due to this, it is less reactive, or it is inactive. It is inactive. Very, very important conditions, main important conditions. So while reading white and red phosphorus, better you create like this and better you read one table, then easy to find out differences. Just I'll draw the white and red phosphorus. Based on that, I'll show how many sigma bonds are present around one phosphorus in white and red phosphoruses. When you asked in KCET examination based on this white phosphorus, in one tetrahedral discrete molecule, how many total number of sigma bonds are present? Here reactivity also very, very important. Why it is more reactive? Bond angle strain is small. That bond angle is here 60 degrees. Here I'll draw here above this table. I'll draw just note on this table also. Last point here. Its white phosphorus structure is like this. P. This is P and this is P. Here P. These are tetrahedrally arranged like this. Here bond and here bond is there. Here bond angle is 60 degrees. Now sigma bonds are 1, 2, 3, 4, 5, 6. So in white phosphorus, white P, that is in P4 molecule, 6 P and P total sigma bonds are there. Very, very important this is. One year asked in CET examination. Whereas in case of red phosphorus, these white phosphoruses are linked like this. Polymeric tetrahedral concept this is. Like this. There is no here like this, here link up takes place. Link up. Again it is phosphorus. Like this. Then again link up takes place. This is the polymeric tetrahedral link takes place and so on. So due to the polymeric tetrahedral link, here its reactivity is generally less. That's why it is inactive, less reactive than compared to the white phosphorus. It is more reactive, less reactive. This is tetrahedral P4, that is red phosphorus, polymeric tetrahedral structures. Very, very important. So better you read this table and remember this table, and from textbook analyze all these points. All are available. Tomorrow I'll explain about preparation methods of hydrates of phosphorus, that is phosphine, then oxoacids of phosphorus, and some important points. Maximum next class Monday I will complete. Okay. So already P block elements inside textbook given, and material, college material also given. Better you follow that material. Okay. Take care.